Hello students, myself Dr. Ranjana Gogoi, Associate Professor of Statistics working at Gorgaon College. Today, I am going to deliver a lecture on least square estimation of parameters, derivation of normal equations, and the estimate of error sum of squares. This presentation is designed for the CBCS Statistics Honors students studying linear models at undergraduate level under Dibrugarh University. The linear model can be expressed as y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta k xk plus epsilon. And here the beta parameters are to be estimated with the help of ordinary least squares when the model is linear in betas but not the axis. To estimate the betas, we will use a sample of n observations on y and the associated x variables. Then the model for the ith observation is yi equal to beta naught plus beta 1 xi1 plus beta 2 xi2 plus dot 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 plus beta k xik plus epsilon I, where I takes the values 1, 2, 3 up to n. So this model 2 can be expressed for each of the n observations as this. Y1 is equal to beta naught plus beta 1 x11 plus beta 2 x12 plus the beta k x1k plus epsilon 1. Similarly for y2 it is beta naught plus beta 1 x21 plus beta 2 x22 plus beta k x2k plus epsilon 2. And for the nth observation yn is equal to beta naught plus beta 1 xn1 plus beta 2 xn2 plus beta k xnk plus epsilon n. So these n equations can be written in matrix form as this one. This is the y vector, column vector. This is the x matrix or design matrix. This is the parameter vector, and this is the error vector. And in compact form, it can be written like that. This y is equal to x beta plus epsilon. So the matrix X in 5 is n by k plus 1 and n is always greater than k plus 1. And rank of X is k plus 1. The X matrix is sometimes called design matrix. Here, the estimates of the population parameters are referred to as beta cap. The criteria used for obtaining the estimates is to find the estimator beta cap such that the sum of the squared residuals, that is summation epsilon I square in scalar notation, is minimum. So the vector residuals E is given by E is equal to y minus x beta cap. So the sum of the squared residuals RSS is nothing but E prime E, and which is, this is the row vector E1, E2 up to En into E1, E2 up to En. This is the column vector. So we have E1 into E1 plus E2 into E2 dot 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 up to En into En, which is a 1 by 1 matrix. So here E denotes the column vector of n residuals y minus x beta cap. There is a distinction between 5 and 6. That is, the 5 is the unknown coefficient beta and the unknown disturbances epsilon appeared in 5. And in 6, we have some set of estimates beta cap and the corresponding set of residuals E. So it should be obvious that the sum of the squared residuals can be written as summation I from 1 to n ei square, which is equal to E prime E. So it is y minus x beta cap prime into y minus x beta cap. And after simplification, it will be y prime y minus 2 beta cap prime x prime y plus beta cap prime x beta cap. The transpose of a scalar is the scalar itself. That is, y prime x beta cap is equal to y prime x beta cap prime. This is nothing but beta cap prime x prime y. To find a beta cap that minimizes the sum of the squared residuals, we need to take the derivative of 8 with respect to beta cap, and then equating to 0 gives the following equation. This is del E prime E del beta cap equal to minus 2x prime y plus 2x prime x beta cap equal to 0. So these are the normal equations, and after simplification we have x prime x beta cap is equal to x prime y. Here x prime x and x prime y are known from our data, but this beta cap is unknown. So if the inverse of x prime x, that is x prime x inverse exists, then pre-multiplying both sides by this inverse give us the following equation: x prime x inverse x prime x beta cap equal to x prime x inverse x prime y. So it is known that by definition x prime x inverse x prime x is nothing but an identity matrix. So this gives us beta cap is equal to x prime x inverse x prime y. So here no assumptions are made to get this beta cap equal to x prime x inverse x prime y. The OLS estimators in the beta cap vector are a linear combination of existing random variables x and y. They themselves are random variables with certain properties. So the expression 12, that is beta cap equal to x prime x inverse x prime y, is the fundamental result for the least square estimators of beta cap of the population parameter beta of the general linear model. Now the mean of beta cap. We have beta cap is equal to x prime x inverse x prime y. So you put y is equal to x beta plus epsilon, the model. So it will be x prime x inverse x prime into x beta plus epsilon. And after simplification, we have beta plus x prime x inverse x prime epsilon, because x prime x inverse x prime x is identity matrix. The expression 13 expresses beta cap as a linear function of the true but unknown parameter beta, and the values epsilon 1, epsilon 2, epsilon n. If we consider the sampling process to be repeated, then the x values remain fixed from sample to sample, but each sample will give a different set of epsilons and hence a different vector beta cap. Now, taking the expected value of both sides, we have expectation of beta cap is equal to expectation of beta plus x prime x inverse x prime epsilon. And here beta is constant parameter, x prime x inverse x prime, this is also a constant, so it is expectation of beta cap is equal to beta plus x prime x inverse x prime into expectation epsilon. But from the assumptions of Gauss-Markov theorem, expectation epsilon is equal to 0, so expectation beta cap equal to beta. Thus it is found that ordinary least squares estimators are unbiased. Now the variance of beta cap. The variance of beta cap can be expressed as expectation beta cap minus beta into beta cap minus beta prime. And this can be expressed in matrix form as like this. So here expectation beta I cap is equal to beta I for I equal to 1 to 3 up to k. And it follows that expectation beta I cap minus beta I whole square is the variance of beta I cap. And expectation beta I cap minus beta I into beta j cap minus beta j is the covariance of beta I cap and beta j cap. Thus the symmetric matrix in 15 contains variances along its main diagonal and covariances everywhere else. We refer to it as the variance covariance matrix of the beta cap, and it is denoted by variance of beta cap. Now beta cap minus beta, this is equal to x prime x inverse x prime epsilon. So variance of beta cap is equal to expectation beta cap minus beta into beta cap minus beta prime. Now we put the expression x prime x inverse x prime epsilon for beta cap minus beta, and we get this expression. Now we use the rule ABC prime is equal to C prime B prime A prime, and noting that x prime x inverse is a symmetric matrix for x prime x, a symmetric matrix. Thus variance of beta cap is equal to x prime x inverse x prime expectation epsilon epsilon prime x prime x inverse. And this is from the Gauss-Markov assumption sigma square in, so it is reduces to sigma square x dash x inverse. Thus we get variance of beta cap is equal to sigma square x prime x inverse. So the variance of any coefficient beta I cap can be obtained by taking the I term from the principal diagonal of x prime x inverse and multiplying by sigma square the variance of epsilon I. Here it is shown that the least square estimators are linear unbiased. The linearity property indicating here that the estimators are linear functions of y as shown in beta cap is equal to x prime x inverse x prime y. Now, to find the estimation of error variance, we proceed as follows. We know that E is equal to y minus x beta cap. So, we put y is equal to x beta plus epsilon and we get this expression by using 5 and 12. And after simplifying, we have epsilon minus x prime x inverse x prime epsilon. And if you take common epsilon here, we get E is equal to I, the identity matrix, x prime x inverse x prime. So this expresses the observed residuals, that is E, as a linear function of the unknown disturbances epsilon. So let A is equal to I minus x prime x inverse x. So it can be seen that A is a symmetric idempotent matrix. For A prime is equal to, again it is A, and A square after simplification we have, this is also equal to A. So thus the sum of squared residuals is E prime E is equal to epsilon prime A epsilon, and for A prime A we write A and we have epsilon prime I minus x prime x inverse x prime epsilon. So now taking the expectation of both sides, we have expectation E prime E is equal to expectation of this expression. And from where after simplification we have, this is nothing but n minus k sigma square. So here x prime x is of the order k, so that x prime x inverse x prime x is an identity matrix of order k. So thus S square is E prime E divided by n minus k. This provides us with an unbiased estimator of the disturbance variance. The calculation of S square of its easily achieved by using it as E prime E is equal to y prime y minus twice beta cap prime x prime y plus beta cap prime x beta cap, and which is equal to y prime y minus beta cap prime x prime y. So SSE is equal to E prime E equal to y prime y minus beta cap prime x prime y. So since x prime x beta cap is equal to x prime y from the least squares derivation of beta cap, and SSE denotes the sum of squares due to errors, thus the estimated error variance becomes S square is equal to y prime y minus beta cap prime x prime y divided by n minus k. So this is the required estimated error variance. So students, I conclude today's lecture here.